So problem 2, they give you a plot of the energy versus the momentum vector k, and you're asked to find to plot the velocity, the acceleration, and the effective mass based on that plot. I'm not going to go through that because you guys, everybody should know from the lecture notes, anybody who's taken the class should know that the group velocity is related to the derivative of that graph, e versus k, and that the acceleration is nothing more than the second derivative scaled by just a factor, 1 over h bar. And the effective mass is the reciprocal of that. So 1 over the second derivative. So you just plot the derivatives, plot the second derivative, and you're done. You're done. That's it. So I'm not spending any time on that problem. Okay, question 1.2. Find the equilibrium electron and hole concentrations and the location of the Fermi lobe for silicon at 27 degrees C if the silicon contains the following concentrations of shallow dopant atoms. 1 times 10 to the 16 per centimeter cube boron atoms for A, and part B, 3 times 10 to the 16 per centimeter cube arsenic, and 2.9 10 to the 16 per centimeter cube boron atoms. Okay, so that's the question. Alright, so there are two things you need to know before you're going to answer this question. One is, what is the intrinsic carrier concentration of silicon? And the next thing you're going to need to know is the band gap. Okay, the band gap for silicon. Okay, so for part A, the first thing you got to recognize is boron is an acceptor. It accepts electrons, so that makes it what? That makes your silicon, when you dope it with boron, that makes it a p-type. P-type silicon. Okay? You should know what that means. Okay, so boron, p-type silicon. You got 1 times 10 to the 16 atoms per centimeter cube. So physically, you actually have in a centimeter cube of your silicon, you have that many boron atoms. Okay. Now, this becomes actually pretty easy. It's simple. So you're trying to find the carrier concentration, the N and P, right? So you want to find how many mobile carriers, and that's equal to the intrinsic number of carriers, or carrier density rather, squared. So using this, we already know that it's p-type. So P is nothing more than this here. Okay? Boom. P equals 10 to the 16th. 1 times 10 to the 16th per centimeter cube. Alright. And what I was saying before, the other thing you need to know is the intrinsic carrier concentration for silicon. This is a good number to know. If you got exams, whatever, you can just bring out the top of your head. You should know this. You know, Ni equals 1.45 times 10 to the 10 per centimeter cube. Boom, should know that off the top of the head. Quick. Okay, you plug these things up in this equation right here, and what do you get? Well, I'll show you what you get. You're gonna rearrange your equation. So you got N equals Ni squared over P. Alright? And boom, Ni squared 1.45 times 10 to the 10 squared divided by whatever we got for P. Same thing, 1 times 10 to the 16. Right? So of course, that's going to just come out simply 2.1 times 10 to the 4 per centimeter cube. That's how many mobile carriers, N-type mobile carriers you have. And of course, it's much less than your p-type because you're doping with p material, boron. It's an acceptor. All right, so that's part A. That's the first part of part A. You also want to find where the Fermi level is. Okay, I can get rid of this now. You know, you got P-type silicon, right? You should know what I'm drawing here. This is a conduction band, and this is the valence band edges. This is going to be your intrinsic Fermi level. But now, since you've got doped silicon, your Fermi energy is going to shift, right? And since you're P-type, you're going to move closer to the valence band. Okay? So, our equation that we know will give us this distance. So, the position of the Fermi energy relative to the center of the band. Alright? Yep, so using our equation, we can find this distance here, EI minus EF, right? That makes sense. And you just plug your numbers in, you just get 0.35 EV. That's simple. So from here to here, it's 0.35 EV. Now for part B, I've already written out the second part of the solution here because it's really easy. It's the exact same as part A, except here's the difference. Okay, in part A, you just had one added, that was boron, right? But now you have boron and arsenic. So you have one donor here and one acceptor right here, and all you do to get the carrier concentration is you subtract them. So you are given, and then you subtract these guys, right? So you're left with 1 times 10 to the 15, and since there's more arsenic, the N-type stuff prevails, right? So this is equal to N. Alright, so the exact same as part 1, except instead of having P, you have N, and this you just take the difference. And then to find P, you simply just say, okay, P is equal to Ni squared over N, and then that's going to give you 2.1 times 10 to the 5 per centimeter cubed. So now, what I've done already up top here, same equation, except last time, since we were P-type, our Fermi energy was down here, closer to the valence band. But now, since we're N-type, our Fermi is up closer to the conduction band. But it's the same difference. This time you have the Fermi minus the intrinsic, since the Fermi is higher, is equal to same thing, except you have N up here instead of P. And you do all the math, and you get 0.29 electron volts. So this here is 0.29 above intrinsic. And you see it's not very much above, but it's enough to make a difference. And that's it. That's the end of question 1.2 in that book. You're done.